our final pattern avoidance. So now we're going to be talking about 2, 1, 4, 3 avoiding linear extensions of a 3, 0 labeled poset. So our first theorem says that a linear extension of a 3, 0 labeled n by n rectangular poset avoids the pattern 2, 1, 4, 3 if and only if there are only 2 active rows at any given point. So an active row is a row where we've selected at least one element from the row, but not all. So if we had selected the 10 and the 11, but we hadn't yet selected the 12, that would be an active n row. So the proof of this is similar to what we saw in the 2, 1, 3 avoiding linear extensions and with our saw blade posets, so I'm not going to go into that so much. But now that we can think of this in terms of active rows, we can relabel our poset so that elements in a given n row all have the same label. And we've decided to do it like this with letters. And so the theorem on our last slide, in terms of our new relabeling, says that we cannot select a z before we've selected all of our x's. So now our linear extensions are sequences of letters, and in particular, it's going to be a sequence of y's along with all of our z's after the last x. So like with the 2, 1, 3 avoiding linear extensions, we're going to think about how adding a row affects the number of linear extensions that we get. So in other words, how can we add a row's worth of elements to a linear extension of an n by n poset and get linear extensions of our n plus 1 by n poset? So the way we're going to do this is by grouping them by their ending, and I'm going to illustrate this with an example. So in our example here, we have a poset where our n is equal to 3, and suppose that our m by 3 poset is this one up to the y's, and our n plus 1 by 3 poset is the total poset. And we're trying to get from the m by n to the m plus 1 by, or the m by 3 to the m plus 1 by 3. So we basically, in other words, we want to add this row of z's to linear extensions of our smaller poset. And the way we're going to, the 3 possible endings we can have are where we have 3 consecutive z's at the end, 2 consecutive z's, or just 1. And so we're going to count these independently. So in our calculations, we rename the total number of linear extensions to A sub m plus 1. And we call the group B sub m plus 1, or B sub m plus 1 counts the number of linear extensions that end with 3 z's. C sub m plus 1 counts the number of linear extensions that end with 2 z's. And D sub m plus 1 for 1 z. And in a process that is explained thoroughly in our paper, if you're interested, we were able to count these in terms of the number of linear extensions of our slightly smaller poset. And we get this system of equations, and when we solve this system, we get a recurrence relation for the total number of linear extensions that avoid 2, 1, 4, 3. So the way we did this is we took the matrix of the coefficients of our system, and doing some work in Mathematica, we get this recurrence relation, which describes the total number of linear extensions that avoid 2, 1, 4, 3 for an m plus 1 by 3 poset. So now David's going to talk a little bit more about these matrices.